Here we're going to look at the basic tool of complex numbers as it applies to math problem solving type problems, like from contests. But before we do that, let's recall some really important and basic definitions. So the first, what is the set of complex numbers in the first place? So we'll take the set of complex numbers to be all numbers of the form a plus bi, where a and b are both real numbers, and I squared is -1. So in other words, I is the square root of -1. Okay, and then we can graphically express a complex number in the following way. So it naturally lives in something called the complex plane, which has a real axis, which we generally put horizontally, and then it has an imaginary axis, which we generally make the vertical axis. So notice I've got a real axis here and an imaginary axis there. That's I times r. And then a number z, a complex number I should say, which is equal to a plus bi. So notice we have gone a along the real axis and then b units along the imaginary axis. So that means this point right here is bi. So that makes this point right here z, which is a plus bi. So in the Cartesian coordinate plane, this would be like a comma b. Good. And then there are two main ways to express a number in the complex plane. One is a rectangular expression, and that's what we've just talked about. So z equals b or a plus bi. And the second is a polar representation, and that goes like this. It's going to be r times cosine theta plus I sine theta. And here r is called the modulus of the complex number. In other words, that's the distance of this complex number from the origin. And theta is called the argument of this complex number. So that's the angle that is made by the ray defined by this complex number and the positive real axis. And we've got some connection between this argument and this modulus and then the rectangular parts of the complex number as well. And those go like this. So the modulus of z, that's the same thing as the square root of z times something called the conjugate of z, which I'm going to go ahead and build this into the definition. So the conjugate of z, which I've underlined there in purple, is this a minus bi. So it's almost the same complex number, except we have negated the imaginary part. But notice if you do this kind of arithmetic application, you'll get this sum of squares, a squared plus b squared. Because notice the cross terms cancel, and then you're left with minus b squared times I squared, but I squared is -1. So there we've got this like modulus of the complex number is given by this thing that looks a lot like Pythagorean theorem. And then next, the argument of the complex number theta has this relationship that tangent of theta is b over a. Okay, good. So now I want to do some basic arithmetic operations on the complex numbers first before we go into looking at contest problem examples. So maybe first we'll look at addition. And really, we want to think about complex number addition as just really combining things with like terms, but also we can think about it geometrically as a sum of vectors. So maybe just a very naive example would be something like this. What if we took 2 plus I and we added 3 plus 7i? So here we would just combine like terms and get 5 plus 8i. Something like that. But now, if we push this into the complex plane and look at what's happening geometrically, it's a little bit more interesting. So notice 2 plus I is maybe this point right here, which I'll call z. So let's, again, maybe call this thing up here z. And then 3 plus 7i, so that's going to be out here 3, and then 7, so that's way up here. Maybe we'll call this point here w. And now what do we get when we add those? Well, it's like completing a parallelogram. So this would be like z, this would be like w, and then if we complete this parallelogram to the end, then the diagonal right there is z plus w. Okay, good. So just like adding vectors. Now what about multiplication? Well, again, a naive example, you would just like kind of FOIL everything out and then add as necessary. So like if we had 3 minus I times 4 plus I, say that. So we would do 3 times 4, that's going to give us 12. 3 times I, that's going to be plus 3I minus 4I from the minus I times 4. And then we've got minus I times I, so that's going to be minus I squared. But we know minus I squared is going to be positive 1 because I squared is negative 1. So we've got negative negative 1. So that's going to give us 13 minus I in the end. Okay, great. Now, what about a geometric application of multiplication? Well, so if we're multiplying by a real number, let's say a positive real number, then that's has the geometric effect of kind of expanding this plane by a factor of that real number. So let's maybe say that we have z here, like that, and then let's say we multiply by a. And let's say a is like bigger than 1. Well, we're going to like complete this ray along z, and then we'll get az out here. And this is here we're multiplying by a real number which is bigger than 0. So notice if a is equal to 1, we land right back on z. If it's bigger than 1, well, we're going to land in this direction. And if it's less than 1, we're going to land in this direction. So it's an expansion or a contraction of the plane. And then another important case to look at is what if we multiply by something of the form cosine theta plus I sine theta. So let's maybe draw that in this way. So if we multiply by something of the form cosine theta plus I sine theta, then the modulus stays the same. And what we end up doing is just rotating this point. So here we'll make sure we're at the same modulus. And now this point right here is z times cos theta plus I sine theta. And the angle right here is given by theta. So in other words, multiplying by this cosine theta plus I sine theta is the same thing as rotation. Now we can put this all together to say that if we multiply by w, then that expands the plane by a factor of the modulus of w, and then it rotates counterclockwise by a factor of the argument of w. Because notice all that's really left here is the argument. The modulus of this cosine theta plus I sine theta is 1. But then all that's left in this case where we have just a positive real number, is the modulus of the number. Okay, so that's a nice geometric interpretation of addition and multiplication. I'm gonna go ahead and clean this up, and we're gonna look at how to divide complex numbers. So now that we've looked at some basic operations on complex numbers, let's talk about division of complex numbers. And I'm gonna do this just by a quick example, and then you can generalize this kind of on your own pretty easily. So let's say we wanna take the complex number 2 plus 3i and divide it by the complex number 5 plus 4i. So the problem here is we know that complex numbers are supposed to be of the form a plus bi, where a and b are real numbers, but that's not what we have here. But now using this idea of the conjugate, which I have over here underlined in purple, we can multiply the numerator and the denominator of this fraction by something that turns the denominator into a real number, which is exactly what we want to do. So let's group these, multiply the numerator and the denominator by 5 minus 4i. And I want to point out that 5 plus 4i and 5 minus 4i are complex conjugates of each other. So let's see what we get here. So this numerator, so that's going to give us 10 from the 2 times 5. And then we're going to have plus 12. So that's our real part. Notice we have minus 12i squared, but that's going to be plus 12. And then next we have plus 15i and then minus 8i. So that's what we have in the numerator. Then the denominator is even easier because we've got this like difference of squares thing happening, but one of our squares involves I, so that really turns into a sum of squares. So this is going to turn into 5 squared plus 4 squared after multiplying everything out. Okay, so let's see. In the end, we're going to have 22 plus, so 7i all over. So that's 25 plus 16. So let's see, 25 plus 16 is 41, like that. But now maybe we want to write this as 22 over 41 plus 7 over 41i. So that would be like the quotient of those two complex numbers. Okay, so let's maybe clean up the board, and then we're going to look at some really important formula known as Euler's formula. Okay, so the last basic thing that we need to look at before we go into some examples is something called Euler's formula. You can derive Euler's formula a number of different ways. I'll let you guys maybe check the details on this however you want to, but what you end up with is e to the I theta is equal to cosine theta plus I sine theta. So if you've got a complex exponential like this, it can be broken down into cosines and sines. So let's maybe like look at a quick example of this. Notice if we have 1 plus I, then that's going to be equal to, well, notice the modulus of this is the square root of 2. So we have the square root of 2. And then we have cosine of pi over 4 plus I sine pi over 4. Now notice that cosine of pi over 4 is 1 over root 2, and sine pi over 4 is also 1 over root 2. So if you multiply the root 2 through, that cancels. But this is our bridge to write this in polar form. So now we can write this as square root of 2 times e to the I pi over 4 using Euler's formula. Euler's formula is also a quick bridge to find some trig identities. Like for instance, if we take e to the I theta and we raise that to the nth power, by exponent rules, we know that that's e to the I in theta. But then, applying Euler's formula to both sides of this, we end up with cosine theta plus I sine theta, all to the nth power on the left-hand side. And then on the right-hand side, we end up with cosine of n theta plus I sine of n theta. Then we can expand this for whichever n that we're interested in, and then extract real or imaginary parts as necessary to come up with some nice trig identities. Like let's say, for example, we set n equal to 2. So that's going to give us cosine theta plus I sine theta squared equals cos 2 theta plus I sine 2 times theta, like that. But now we can FOIL out the left-hand side. Notice we're going to get cosine squared theta minus sine squared theta. So that's going to be the real part from cosine times cosine, and then I sine times I sine. And then we've got the cross terms, which are going to be equal to 2I cos theta times sine theta. But now we can equate the real part on each side of the equation and the imaginary part on each side of the equation to come up with the well-known trig double angle identities. So here we've got cosine squared minus sine squared. So that's going to be cosine 2 theta. So those two are equal. And then we know that 2I cosine theta sine theta is going to be the same thing as I sine 2 theta, just by extracting real and imaginary parts. So now we could write down that this implies that cos 2 theta equals cos squared theta minus sine squared theta, and also that sine 2 theta equals 2 times cos theta times sine theta. Great. Now you can even do this for different angles. So let's maybe fit that in up here. We can just expand that 2 different ways. So we can expand e to the I alpha times e to the I beta. So on the one hand, that's e to the I alpha plus beta. And then on the other hand, we can expand this using Euler's formula. So over here on the left, we have cosine alpha plus I sine alpha times cosine beta plus I sine beta. And then over there on the right, we're going to have cos alpha plus beta plus I sine alpha plus beta. Now we can expand the left-hand side of that equation, extract real and imaginary parts, and compare it to the right-hand side of the equation, and come very quickly up with some formulas like cosine alpha plus beta equals some stuff. I'll let you guys check what exactly you get by multiplying out that left-hand side of the equation. Okay, so now let's go ahead and clean this up and we'll look at some nice examples. Okay, for our first example, we're gonna calculate a double angle formula for tangent. And even though we just looked at Euler's formula, we're gonna do this a slightly different way, just being motivated by the geometry of the polar form of a complex number. But now we're gonna wanna find the simplest complex number whose argument is theta. And we can do that via looking at this formula down here. So we know tangent of theta, in other words, tangent of the argument is equal to b over a. So we might as well set z equal to 1 plus tangent theta times I. In other words, a is being played by 1 and b is being played by tangent of theta. But now under this setup, we can say that the argument of z is equal to theta. Great. But now we can jump from there to say that the argument of z squared is going to be equal to 2 theta. Because that's how arguments work. Just think about the Euler's formula with e to the I alpha and e to the I beta. If you multiply those two numbers, you add the angles or you add the arguments. So if you square a complex number, you're going to add its argument with itself. It's like from that rotation principle. But now I want to flesh out this z squared object a little bit. So here we have the argument of 1 plus tangent theta times I quantity squared, like that. Good. But if we calculate that, we have the argument of, now if we multiply out this right-hand side, we'll get 1 minus tangent squared theta. So that's what we get for the real part. And for the imaginary part, we'll have plus 2 times I times tangent theta, like this. So we have the argument of that complex number. So just to reiterate, what we have going on here is 2 theta equals the argument of this complex number, which has real part that, which I'll call A, and it has imaginary part this, 2 times tangent theta, so I'll call that B. Good. But now we're going to use the fact that tangent of the argument is equal to b over a. And that follows from this, just where theta has been replaced with 2 theta or something. So let's take the tangent of both sides. So tangent of 2 theta, that's tangent of the left-hand side, equals the imaginary part divided by the real part. So that leaves us with tangent of theta times 2 over 1 minus tangent squared of theta. And that derives a semi-familiar double angle formula for tangent. Okay, so let's go ahead and get rid of this and we're going to look at another example. Okay, for our next example, we're going to show that if m and n, which are natural numbers, can be written as the sum of squares, so can m times n. So let's just look for example. We know the number 25 can be written as the sum of squares because it's equal to 3 squared plus 4 squared. Well, that's just part of a Pythagorean triple, but it turns out that there are lots of numbers that can be written as sums of squares that are not Pythagorean triples. Like for instance, if we take 2 squared plus 7 squared, so that's going to be 49 plus 4, so that's going to be 53. So 53 is one of these numbers that can be written as a sum of squares. But here, this is saying that the set of the sum of squares is closed under multiplication. That is, if you've got one and you've got another one, and you multiply it, you've got a new number that can be expressed as a sum of squares. Okay, good. So maybe let's get to it. So how do you do this? So you're going to take m and you're going to write it as its sum of squares, a squared plus b squared, where those are all natural numbers. Then we'll do the same thing for n. That's going to be equal to c squared plus d squared. So using integers, these expressions are not immediately factorable. But if we include the complex number I along with the integers, sometimes called the Gaussian integers, we can immediately factor these. Notice this first one is going to factor like a plus bi times a minus bi, like we've seen. And then the second one is going to factor like c plus di times c minus di. Good. And this factorization has the seeds of exactly what we want to express m times n as a sum of squares. For instance, if I take this number right here and this number right here, a plus bi and c plus di, and I multiply those, that's going to be a big tool for writing m times n as this sum of squares. Okay, so let's go ahead and do this. So let's set z equal to a plus bi times c plus di. And then notice that we can multiply this out. This is going to be ac minus bd. Again, that would be the a times c and the bi times di. And then next we're going to have plus ad plus bc times I. Like that. Now, I want to go ahead and write that as capital A plus capital B times I, where I just absorb all of these numbers into capital A and all of those numbers into capital. And those are still integers because they're combinations of integers. Now, the next thing that I want to notice is if I take z times z bar, on the one hand, I'm going to get m times n, because z times z bar is just the multiplication of this line times this line. But then on the other hand, it's going to be equal to a plus bi, where I have capitals, and capital A minus bi, where capital A and B are defined like that. But this is equal to capital A squared plus capital B squared. So I have exhibited the product of m and n as the sum of two squares, which is exactly what we wanted to do. Okay, so I'll clean this up. Then we're going to look at the notion of roots of unity before our last example. So we're going to finish this video off with the notion of the nth roots of unity, as well as a problem from the USA National Math Olympiad. Okay, so we say that zeta is an nth root of unity if it satisfies the equation zeta to the nth power equals 1. So these are like the nth roots of the number 1. And here's a fact, and so we're not going to prove this, but you could grab a proof for this pretty easily, and that is the nth roots of unity are these following n complex numbers. And so there's 1, and then there's zeta, which is equal to e to the I 2 pi over n. And then there's zeta squared, zeta cubed, all the way up to zeta to the n minus 1, where what I'm doing is I'm squaring this complex number e to the I 2 pi over n, cubing it, and so on and so forth. So notice I've got the 0th power of zeta, the first, the second, the third, all the way up to the n minus first. And those are the n total different nth roots of unity. Okay, and then a really important factorization involving these nth roots of unity goes like this. So we've got z to the n minus 1 factors as a product of z minus each of these roots of unity. So we've got z minus 1 times z minus zeta times z minus zeta squared, all the way up to z minus zeta to the n minus 1. Now, if we go ahead and take both sides of this equation and divide it by z minus 1, well, the right-hand side is going to look essentially the same, just without a z minus 1 as part of this product. But the left-hand side is going to simplify to this object, and this is an important formula. So z to the n minus 1 times z to plus z to the n minus 2, all the way down to z plus 1 is z minus zeta times z minus zeta squared, all the way up to z minus zeta to the n minus 1. Okay. But now, if we evaluate the right-hand side of this equation at zeta, notice this first one is zeta minus zeta, which is 0. And then the left-hand side of the equation will be this sum of all the roots of unity. So notice we have zeta to the n minus 1 plus zeta to the n minus 2, all the way down plus zeta plus 1. That equals 0. Okay, so for our example, we want to look at, like I said, this problem from the USA Math Olympiad 1976, and we want to have polynomials P, Q, R, and S that satisfy the following equation. So we've got P evaluated at x to the fifth plus x times Q evaluated at x to the fifth plus x squared times R evaluated at x to the fifth equals x to the fourth plus x cubed plus x squared plus x plus 1. And what we want to show is that x minus 1 is a factor of p of x. In other words, p of x can be written as x minus 1 times a of x, where a of x is another polynomial. But that is equivalent to the following statement, that p evaluated at 1 is 0. And that's exactly what we're going to show, that p evaluated at 1 is 0. So how we're going to do this is we're going to take this starred equation and we're going to evaluate this starred equation at all of the roots of unity. And which roots of unity? Well, the fifth roots of unity, because notice we've got an x to the fifth here. So any fifth root of unity to the fifth power is going to be 1. And then any fifth root of unity put into this polynomial right here is going to be equal to 0 by this observation down here. Okay, so let's maybe look at all 5 equations. So let's say we have x equals 1. That's our first equation. So notice that's going to give us p of 1 plus q of 1 plus r of 1 equals, so that's going to be 5 times s of 1. So in fact, this is not super helpful, and we don't even really need this one. So this is not helpful. I mean, maybe it was useful to look at it, but it's not helpful for finding our solution here because it doesn't allow us to get rid of anything. But now notice if we look at the other fifth roots of unity, so the ones that are not equal to 1, those are the ones that equal 0 when we plug them into this x to the fourth plus x cubed plus x squared plus x plus 1 object. So that's what we want to look at. So here, let's go ahead and set zeta equal to e to the I 2 pi over 5. So in other words, this is a fifth root of unity. Sometimes we would say a primitive fifth root of unity, but since 5 is a prime number, that doesn't really make a difference. Okay, so let's go ahead and look at the case when x is equal to zeta. So this equation is going to turn into p evaluated at 1 because zeta to the fifth is 1, given that it's a fifth root of unity, plus zeta q of 1 plus zeta squared r of 1 equals 0. We know it's equals 0 because, again, when we plug that into this thing right here, we get 0 by our earlier discussion. Now let's look at the other cases. So x equals zeta squared. So that's going to give us p of 1 again. Again, if we evaluate this at zeta squared, we're going to get zeta to the 10th, but that's zeta to the 5th squared, but that's 1 squared. So we're good to go there. And now we have zeta squared q of 1 plus zeta to the fourth r of 1 equals 0. So that's what we get for the zeta squared. Let's look at the zeta cubed. So here we're going to get x equals zeta cubed. So again, we'll have p of 1 plus zeta cubed q of 1 plus zeta to the 6th. But what I want to notice over here is that zeta to the 6th is the same thing as zeta times zeta to the 5th, which is equal to zeta because zeta to the 5th is equal to 1. So in fact, the exponents here are working modulo 5, if you want to think about it that way. So here we've got zeta times r to evaluated at 1, and we have this is equal to 0 again for the same reason. Now we've got one more to check, and that's x equals zeta to the 4th. So that's going to give us p of 1 plus zeta to the 4 q of 1 plus zeta. So this is going to be cubed r of 1. And that's because we get zeta to the 4th squared. That's going to be zeta to the 8th. But we can reduce that using that trick over there to zeta cubed. Great. And now we have this is equal to 0. Now we've got these 4 equations. But now we can just add these equations. So here we're going to get p of 1, p of 1, p of 1, p of 1. So notice that's going to be 4p evaluated at 1. But now notice that adding up down here, we have zeta plus zeta squared plus zeta cubed plus zeta to the fourth. But that's almost all of this. We're just missing a 1, which means that if we add these up, we'll get a factor of -1. Again, kind of by rearranging this equation. So this is going to be minus q of 1. And then similarly here, we'll have minus r of 1 equals 0. Okay, good. So that leaves us with this equation, 4 times p of 1 equals q of 1 plus r of 1. And we're not quite done, but we've arrived at a useful equation. Okay, so I'm gonna go ahead and clean up the board, keep what we need, and then we'll finish it off. Okay, on the last board, we had this fifth root of unity, which we called zeta, and we arrived at some equations involving our polynomials evaluated at 1, along with these fifth roots of unity. And so I've rewritten these a little bit, but it is equivalently what we had before. Okay, so first what I want to do is look at what these first two equations can give us. So let's take these first two equations and think about minus p1 is equal to minus p1, which means this right-hand side equals this right-hand side. Both of these right-hand side are multiples of zeta, so we can factor a zeta out, and that gives us this equation, q evaluated at 1 plus zeta times r evaluated at 1 equals zeta times q evaluated at 1 plus, so if we factor a zeta out of it, that'll be zeta cubed evaluated at r times r evaluated at 1. So that's what we get from those two. And then likewise, we can do that with this first equation and this third equation, and that's going to give us another equation involving r1 and q1. Again, setting this minus p1 equal to this minus p1, and we can also factor a zeta out, just like we did before. So notice that's going to give us q1 plus zeta r1 equals zeta q1 plus r1, like that. Good. Now what I want to do is solve each of these for r. So let's see if we can do that. So notice solving this one for r is not too bad. I can move this r over and this thing over. So that's going to give me r of 1 times 1 minus zeta, q of 1 times 1 minus zeta. Okay, well that's pretty nice because that tells us that r evaluated at 1 equals q evaluated at 1. Okay, so now we can plug r evaluated at 1 equals q evaluated at 1 into this equation, and that's going to give us, so q evaluated at 1 plus zeta times q evaluated at 1 plus equals zeta times q evaluated at 1 plus zeta cubed evaluated at q evaluated at 1. But now we can move everything over to one side of the equation, and that'll give us something like q of 1 times the quantity 1 plus zeta minus zeta cubed equals 0. Good. But then we know as a fact this is not equal to 0. Again, 1, so we've got zeta minus zeta, so that is 0, but then we've got 1 minus zeta cubed, but we know zeta cubed is not equal to 1 because it's a fifth root of unity, so that means this thing right here is not equal to 0, which tells us that q must be equal to 0. So, sorry, q evaluated at 1 must be equal to 0. But then likewise, r evaluated at 1 equals 0. But that means their sum is equal to 0. But that means that 4 times p of 1 is equal to 0, but that means that p of 1 equals 0, which is exactly what we needed to show. And that's a good place to stop.